Hello and welcome to another Dr. Sarkis video. So what we're doing now is we're just going to show that the step we have taken last session can be applied to any other term of x. So it can be, we can apply a derivative to 5x to the power of 7. It will work the same, but we know that with the limit definition I've just shown you, things kind of take time because we need to expand the brackets first and then look at where h approaches 0 and how that affects our answer, and how we need to divide everything by h, and sometimes we have to simplify an expression in order to be able to divide by h, and so forth, and that takes time. So there's something called the power rule, which I'm going to prove now, which works for, again, any a times x to the power of n. And just like I gave you a little spoiler here in the last session, I said that for mx to the power of n, and actually it would probably be neater if I just say a times x to the power of n. The derivative would be an times x to the power of n minus 1. So we're going to be using a very important way of proving things in calculus and in maths in general, and that technique really is called proof by induction. So when you prove something by induction, it means there's a statement, and you want to prove a statement, and you want to prove that it works for all possibilities of that number n. So what you do is you, assuming that statement holds for n equals a certain number, preferably 1 because it's easiest to prove, then you're going to assume that it's also correct for n equals k plus 1, so n equals a different number that's bigger than that previous number. And then showing that assumption is correct, you're going to essentially have a concluding statement which says that the statement is correct because we have shown that it holds for the assumptions we have made. So therefore it should hold for other possibilities of n. So what I'm going to do now is I'm just going to quickly show you an example of this with the power rule, which is a very, very powerful rule as its name says. It's a very powerful rule in calculus, and it's essentially the basis of differentiation, the basis of integration, and yeah, well, calculus gets harder than that, but in reality this is probably the most important differentiation we're going to learn. So we're going to delve into it. Okay, so we have a limit. We're going to assume that we're going to try to prove the statement ax to the n prime, which means the derivative of that is an times x to the power of n minus 1. We've shown that it's true for 2x, x squared turning into 2x by differentiation. And now we're just going to kind of do it in a different way, starting with n equals 1. So n equals 1. So that's the easiest, that's elementary, but that's the basis step for induction. So h approaches 0, and the function we're having here is essentially just ax, because n is equal to 1, so there's no need to have an exponent. So we have that, but really we need to start with h, because we have this definition of a derivative. We're starting with h and then we're subtracting by the original function where h is not part of the input. So then minus ax over h. It takes time to write over its limbs. Okay. Ax plus ah minus ax. You've used the trick. Just minus both sides here because they cancel out. Then we have h. It doesn't even matter that h approaches 0 because essentially we just end up with an a regardless. So we have a. Woohoo! That's the first step done. And what is a? a is the same thing as a times x to the power of 0, right? So then we have taken an a, x to the power of 1. We've done exactly what this formula does, which is subtract the first move the exponent to the coefficient of x, and then minus the exponent by 1. So great. So then we removed it. We removed the 1 here. So we subtracted by 1, and we removed that original 1 to here. It didn't really change much because it's 1 times something itself. And then what we ended up with is 1 times a times x 0, and x to the 0 is 1. So 1 times a times 1 is equal to a. I think we can all agree on that. So then this is our first n equals k. K is equal to 1. So that's our first step in induction. Now what happens when n equals k plus 1? What happens when n is equal to 2? So yeah, we already kind of proved it in a way in the last video, and I'm just going to iterate. So we have a times x plus h, not n, to the power of 2, but that 2 is n. That's our expression from a statement, minus ax to the 2 squared divided by h. And again, what we have here, I'm not going to write the limit here, but it takes time, but we have ax, we have well actually no, I'm going to write the full expression here. You know what, I just write the whole thing. Okay, so then we have a times x squared plus 2hx plus h squared minus ax squared, or that divided by h. So then, just going to move the paper a little bit. So then we have, first we expand the brackets, or we multiply the brackets. So then we have every term essentially having an a. So it's quite funny because you can save it. But this is ax, this is hax, and this is r. Okay. So then, all of that divided by h. First of all, as we did in many other cases, we just remove it. ax, the first nomial here, because here it cancels out. And then we just we divide both sides by h. So then we have a limit as h approaches 0 of 2 ax plus ah, and that's it. And h approaches 0, so it doesn't matter what a is equal to, because eventually h is going to be 0, and then it doesn't matter, it just all turns out to be 0. So then we have 2ax, and what is 2ax? 2ax is the same thing as, well, let's see, let's kind of use our reverse engineering technique here, and look at what we started with. We had x squared, ax squared, and we turned that by the power rule into 2 times ax 2 minus 1. So that should be the same thing as 2 ax to the 1 equals 2ax. And that's exactly what we got here. We got 2ax. So then if the statement holds for n, for k equals 1, and it holds for k plus 1, so implying that k can be anything, and you just keep plusing it by 1, keep adding 1, and then that k can be anything. So for any k plus 1 could walk. So then it just kind of creates this infinite loop of values for which this power rule walks. So it walks for any integer essentially. Any integer when n is equal to, n is greater than 1. So this is pretty amazing, I think. And yeah, so this is our new rule. For any ax to the power of n, differentiation would mean getting the an x to the n minus 1 term here. So that's a very important rule. I'm just going to show you really quick that also when we have two other rules. We have the addition rule and we have a subtraction rule, which we don't really need to delve into the subtraction rule, but addition rule just quickly showing you. So if we have two limits, actually if we have, say, I don't know, x squared, then we have 5x. So essentially, when you work out the differential, the derivative, the same thing of this term here, that'll be the same thing as working out the derivative of this plus the derivative of this. I'm not going to show you exactly like the proof of this because it's a bit pointless, but because it's just obvious, because both of them can be expressed as limits, with h being the denominator. So if you're adding two things with the same denominator, then it's the same thing as condensing those two into the same fraction. So yeah, so that's our proof. So for induction of the power rule, and I'll see you in the next video. Hopefully we'll move into more advanced differentiation rules. See ya.